important aspect of coding is the ability to approach the Shannon capacity. So Shannon in the 50s came up with his Shannon limit, and we had no idea then of how to achieve that limited performance. So given that we cannot go beyond, how do we get close to that limit? But today we have common codes which can indeed approach the Shannon capacity. We call these capacity achieving or capacity approaching codes. And we can get very, very close to that. And I'd like to show you an example today out of Matlab on the digital video standard, digital video broadcast standard for error correcting codes. They're not convolutional codes. I think they're block codes, but they're concatenated codes, and they're just capacity achieving. So I'd like to just leave you with that because I like to say error correcting codes for me are like magic. They just work so well. And I'd like to just leave you with an appreciation for how phenomenal these error correcting codes really are. So let's just quickly return to the idea of Shannon capacity. Remember, Shannon's law says the capacity of a channel with a certain signal to noise ratio and a certain bandwidth can be given by this very simple expression, and this is for an additive white Gaussian noise channel. So the idea is that we have the ability to send C bits per second with the probability of error as small as we want, provided we have sufficient SNR and bandwidth. And we went through all the equations, an equivalent way of writing that simple expression for Shannon's limit, and we found that if we let our channel capacity, our channel efficiency go to 0, so like a really, really, really bad efficiency, that we could get to an EBN0 as low as minus 1.6 dB and still have reliable communications. Kind of phenomenal that the noise can really clobber your signal and you could still good performance. So if you remember, we divided the SNR, the bandwidth efficiency plane, into two sections, that on the practical side of the Shannon limit, which is the curve there, and the unattainable region on the other side of the limit. And, again, going to spectral efficiency of 0, we got this asymptote at minus 1.59. And here, I'd like to show you one of the codes that could indeed approach this Shannon capacity. So we're going to see a demo in Matlab, and in the demo in Matlab, we're going to look at QPSK in particular. So in order to see what we're doing in this demonstration, I've just plotted Shannon's law again, only this time on a linear scale in terms of the spectral efficiency. And here is EB over N0 on the x-axis. So if I look at QPSK, the very, very best I could do, no coding, would be 2 bits per second. 2 bits per second per hertz. This is spectral efficiency. And Shannon says I could get arbitrarily small bit error rate even at something like, let's say 1.5, 1 3/4, something like that. Now if I use a forward error correcting code, of course I'm going to look now at an example with a rate 1/2 code, which means the best spectral efficiency I could get would be 1 bit per second per hertz for this QPSK. But what I'm going to show you is I can get really, really close to this 0, actually have noise just as high as my signal, and still be able to have good communications. So I'm going to be looking at QPSK. QPSK, there's just the 4. Well, it doesn't look very straight, does it? 4 points. Okay, so the distance to the origin gives you an idea of how strong the signal is. The noise cloud around that is going to be just as big as the signal if I have 0 dB EB over N0. And what we're trying to say is that even in this condition where the noise is just as big as the signal, that we're still going to be able to get reliable communications with probability areas small as we like. So that's what a channel capacity achieving error correcting code would do. So let's take some time to look at this Matlab example to see such a code. So I said it was a digital video broadcast. It's a IEEE standard using some concatenated codes. It's used for satellite video. The two codes that are concatenated are a BCH code and an LDPC code, some very large block codes. So a block before and after encoding, so we can see this is a 1/2, and this is a very low rate code, so very low addition, but somehow the combining of these two block codes combined with interleaving is going to allow us to do decoding. And this has got some turbo decoding where I do the inner code, outer code, feed my decisions back and forth, and do many iterations in that process until I correct as many errors. So, you know, there's high latency in this approach. There's also convolutional codes would have low latency. So there's trade-offs. Just like we had all kinds of modulation formats so that we could cover all kinds of situations, it's somewhat true also with coding. But in this example, we're not caring about latency. We're pretty good on complexity. We're going to go through like 50 iterations, I think, in order to get back and forth to make this decision free. So very high complexity perhaps, but manageable. And in this example, we'll show you how close we can get to the Shannon limit. So before I get into Matlab, I'll just summarize the results for you so you can appreciate what you're looking at. And this is the QPSK without coding, which you see in blue here. And this in yellow, poof, is the error correcting code version. Okay, so once I have the FEC added to it and I trace the bit error rate as a function of SNR, you can see we're getting very close to the limit. Remember that for QPSK with 1/2 rate code, that Shannon's limit said that we should be able to get down to something like 0 SNR. And in this case, we're going to get within like 0.8. We're going to get somewhere like within something smaller than a dB. So we're going to be very, very, very close to the Shannon limit, which if we looked at 10 to the minus 6 as our level, that would mean that we were getting more than 10 dB gain from using coding. So instead of requiring something like SNR of something like 10 dB, we're only needing something like 1 dB in order to achieve that level of service. Let me just say also, where is it that this intersection occurs? Remember, there's always a FEC threshold, and it's really, really high for this code, very, very high performing code, which means as long as my bit error rate is lower than 5%, as long as it's less than 1 in 20 errors, I'm going to be able to see improvement with this code. And indeed, the code could be very, very strong. And you can see how sharp that is. Now, let's change the scale. This is the scale where I see the typical uncoded performance, and if I change the scale, now I'm looking at something very fine between 0.2 and 1 is now the range. So I've zoomed in at where this fall off is. But of course, much, much steeper coded. We still have a waterfall shape, but the waterfall shape is much more steep decline with an error correcting code. And so as we look at this system, we'll see that, you know, as long as we're above like 0.8, we're getting very good performance from this code. So I'm going to open up the Matlab demo. You can look for it yourself online. This is the digital video broadcast. It's run in Simulink. In here I can set the parameters for the model, so that's where I'm going to play a little bit with the signal to noise ratio, so I can see where that knee happens in that waterfall fall. Here you can see you're generating bits, you're buffering them, you're putting them into your first layer of encoding, then you're going to your second layer of encoding. You're going into QPSK modulation, additive white Gaussian noise. Here we're going to monitor, you know, what exactly is the signal to noise ratio. We'll set it here, and then we'll validate it here. Here we're going to look at the constellation, the received constellation with the noise present, and see how bad it is. Here we have the demodulation and the decoding. And you can see there's an inner decoding and then an outer decoding. And this is going to tell us finally what is the bit error rate. here there's these second layer with these packets that might have been an error, but then we're going to get them corrected. And so we're looking at something here. It's going to tell me how many bits I examined, how many errors that were counted when I've transmitted that many bits, and then it's going to calculate based on number of errors divided by number of bits what the bit error rate is. And we will see that if I'm above a certain level, that I'm going to get virtually no errors, arbitrarily low bit error rate. And but at a certain EBU over N0, that's going to just disappear. And then when I cross over that threshold, we're going to we're going to start seeing the bit error rate will suddenly skyrocket. So let's have a look at it. Remember, this is the 4 points that are transmitted, and when I look at the received constellation, I'm going to see a cloud, which is huge. I can't see the 4 points at the endpoint because I'm operating at a signal-to-noise ratio where the noise is on the same order of magnitude as the signal power itself. So let's have a look now at the Matlab demo. So here on the left, you'll see that I have the Simulink simulator open, as we saw before in the slide I was presenting. Let's see if I can open it a little bit more for you. It doesn't seem to want to let me. There we go. And on the right here, well, that's coming from this part, I have the constellation where I'm going to be displaying it here on the right for you. And here we can see the SNR now is set at 0.8 dB. And I'm going to go into the parameters, and I'm going to maybe set it to 1. Here's the number of iterations for the decoding process. Of course, if I made that smaller, the code would, the error performance would not be as good, but we're going to leave it there for now. And I'm going to run my simulator, and it starts out, builds up the received constellation, and now you can see here it's counting the errors. It went up to 10 to the 5th bits, and it counted no errors. So it's being able to correct all those errors. There were 3 packets, I think packets in error, no errors there as well. So now I'm going to change this to, like, instead of 1, I'm going to put 0.5, and so half a dB difference in the signal-to-noise ratio, and I run it again, and now the cloud looks similar because it's not terribly different, 0.5 versus 1, but we can see now that we're having a huge number of errors, and now my error rate is going up to something close to 10%. So it's very, very sensitive to the threshold value here of the error rate. And you can play with this, and I think if we get something like 0.75, I'm not sure which way we're going to fall on it now. Try it again, and see how many errors we're counting. No errors, so there they go, fell off the edge. Now we're getting sort of near the edge of it. It's not atrocious, but we're getting very, very close. So it becomes very touchy at the 0.75, and it's fun to play with the number of iterations, so that has to do with the complexity and the latency and how long until you can get a decision to come out, to get a feel for how these concatenated codes can be used to really improve performance tremendously.